Hello everyone, let's start with this lecture. We study the time domain analysis module of discrete systems for linear systems of signals. We are starting part 5 today, study on time domain analysis method of discrete system. The fifth content discrete LTI system unit sequence response. First question, what is the unit sequence response of the system? That is, when the excitation function is delta of k, zero state response on the system. We call this the unit sequence response. Let's write it in terms of h of k. Now let's look at a specific example. Solve the unit sequence response of the system as shown in the figure. To solve this problem, the first step is we want to represent the system as a mathematical model. Then you need to represent the system as a difference equation. So how do we solve the difference equation? We need the basis. The first module we cover is the simplification of the block diagram. First, let the input of the leftmost delay cell be set. Its intermediate variable is S of k. So obviously, after the first delay unit, the intermediate variable is x of k minus 1. After the second delay unit, the intermediate variable is x of k minus 2. Then write the equations according to the summator. After you write these two equations, let's get rid of the intermediate variable x of k and the intermediate variable x of k minus 1 and the intermediate variable x of k minus 2. So that's the difference equation. So now that we have an expression for this difference equation, let's solve for the unit sequence response of the system. Let's analyze this. You want to find the unit sequence response of the system. We can do it in two parts. The first part of the system sets delta of k only. So the second part, the system acts on the excitation minus f of k minus 2, and this excitation is also minus delta of k minus 2. Based on the linearity of the LTI systems, we can see between h2 of k and h1 of k satisfies the relationship. So the unit sequence response h of k of the entire system can be obtained by the subtracting h1 of k from h1 of k minus 2. This conclusion is based on the linear relationship satisfied by the discrete system and the analysis of time invariant characteristics. This is a basic analysis of our thinking for the first example. So let's do another example, as shown in this figure. This is a discrete system unit that we are given. The known system block diagram is shown in the figure. Find the unit sequence response of the system. First question, we are going to write down the difference equation for the system. This difference equation we started with the adder. Can see between y of k, f of k, and the other shifted sequences. That satisfies an equation like this. Let's put it in order. Then we can see the expression of h of k for the corresponding difference equation of the system block diagram. So let's solve this difference equation. Find the unit sequence response. So when the excitation function is delta of k, what is the unit sequence response to the system? Bring incentives in. The equation becomes something that looks like this in terms of h of k. So when k is greater than 0, the difference equation becomes a homogeneous difference equation. We know from the characteristic equation that the characteristic root is a triple root. Therefore, the expression of unit sequence response is h of k is equal to c1 times the square of k plus c2 times k plus c3. So, the undetermined coefficient here is c1, c2, and c3. How to solve it? Let's see. The solution to the undetermined coefficient is obtained according to what the zero state response means. The initial state is 0, so that means that h of minus 1, h of minus 2, h of minus 3 is equal to 0. Let's take that to the difference equation up here. We can iterate over the values of h of 0, h of 1, h of 2. Let's say that h of 0 is equal to 1, h of 1 is equal to 3, h of 2 is equal to 6. So let's take this initial value. In the expression we just got for the unit sequence, we can get the specific values of C1, C2, C3. The expression of the unit sequence response is obtained. So you can see that through this process, the excitation delta of k acts on the system. Its specific function is reflected in the change of initial conditions. So when k is greater than 0, the form of the difference equation is kind of like a homogeneous solution. This is a general way of solving unit sequence responses. The second question is about a single-step response. So, what is the unit step response of the system? The unit step response is for LTI discrete systems. When the excitation function f of k is equal to the unit step sequence epsilon of k, zero state response generated by the system. We call this the unit step response, expressed in j of k. So what kind of relationship does this satisfy? We can see that the relation between epsilon of k and delta of k satisfy the summation, equivalent to the superposition of shift sequences, which can be regarded as delta of k. So based on the properties of LTI systems, the relationship between the unit sequence response h of k and the unit step response j of k is linear. This relationship is because the sum is sometimes used less, so this formula is used less. In general, we use the difference form of j of k and j of k minus 1. The expression of unit sequence response h of k is obtained. This relation is used relatively often. I want your attention. And the third area we are going to look at is chirality and stability of the system. What is a chiral system? A system where the change in output is not ahead of the change in input. For LTI system, it is necessary and a sufficient condition for a chiral system when k is less than 0, the unit sequence response h of k is 0. necessary and sufficient conditions for stability. The unit sequence response is required to be absolutely summable. This is an important way to judge the chiral stability of the system. It also means the unit sequence response h of k, it plays an important role in system analysis. Now, let's look at a specific example, an LTI system. The expression for its unit sequence response to h of k is given. Let's talk about chirality. Expression according to h of k, because of the epsilon of k effect, so it belongs to a system that has causes. When k is less than 0, h of k is absolutely equal to 0. So, the system is chiral. Let's talk about its stability, and we're going to test with the notion that h of k is absolutely summable. After the solution analysis, the system converges when the absolute value of A is less than 1. So the absolute value of A is less than 1. The system is stable. So chirality and stability of the system. More detailed analysis method. We will discuss this in detail in part 7. That's all for today. Thank you for listening, and see you next time.